start with the experiment that broke physics. You fire electrons, one at a time, at a barrier with two thin slits, and you record where each one lands on a screen behind it. One particle, then a long wait, then the next. Nothing that could bump into anything else. Now watch the screen fill in. With 11 electrons, it is just scattered dots. At 200, still noise. At 6,000, a hint of something. At 40,000, you can see it. And at 140,000, it is unmistakable. Bright bands and dark bands, an interference pattern, built one lonely particle at a time. Sit with how strange that is. Each electron crossed the apparatus alone, yet the pattern that emerges is the pattern of waves passing through both slits at once and interfering. So each electron, in some exact sense, went through both slits and interfered with itself. This is not a quirk of the equipment. It is the cleanest evidence we have that the universe, underneath, does not keep a ledger of definite positions. It keeps a ledger of amplitudes. Numbers that can add up or cancel out, and it only turns definite when you look. Quantum computing is what happens when you stop being a spectator to that and start using it on purpose. Here is quantum computing in one sentence. You arrange amplitudes so that the wrong answers cancel and the right answers reinforce. That is the whole game. Everything else is machinery for doing it. So let us draw the one picture this series comes back to again and again. A quantum state is a row of bars, one bar for each possible answer. The height of a bar is how much amplitude that answer carries. And on top of every bar sits a little arrow, showing the amplitude's phase, the direction it happens to point. Now, why arrows? Because amplitudes add the way arrows do, tip to tail, not the way ordinary numbers do. Point two arrows the same way and they stack into a longer one. That answer gets a taller bar and becomes more likely. That is constructive interference. Point them in opposite directions and they cancel. The bar collapses to nothing, and that answer simply never happens, even though each arrow on its own was perfectly real. That cancellation is the whole trick. A quantum algorithm is a careful arrangement of gates whose only job is to make the arrows on every wrong answer point against each other, so that when you finally measure, what is left standing is the answer you were after. It sounds like it should take exotic hardware to even think about. It does not. Everything I just described is small. A single qubit is two complex numbers, the amplitude of 0 and the amplitude of 1, two numbers. A gate, the thing that transforms a qubit, is a 2 by 2 matrix. And a register of several qubits is just an array of amplitudes, one for every combination of zeros and ones. A state is a vector, a gate is a matrix. Running a circuit is multiplying them together. That is linear algebra you already know. Which means you can build the entire thing in plain Python, on top of NumPy, and watch every piece work. This series does exactly that, inside a small package we write ourselves, called QFS. A fresh qubit is one line, an array of two amplitudes, starting in the state 0. Apply the Hadamard gate, which is a single matrix multiply, and the two amplitudes become equal. A clean superposition. Square the magnitudes, and out come the probabilities. Nothing is hidden in a basement. There is no framework doing the real work offstage. The array on your screen is the quantum state, all of it. So here is the road ahead. We start with a single qubit and its first gate. Then we tensor qubits together and meet entanglement, where two qubits share a state that neither one holds on its own. We build circuits and make interference do real work. Then the famous algorithms. Grover's search, which steers amplitude toward a needle in a haystack. The quantum Fourier transform, which reads a hidden frequency out of a pattern of phases. And Shor's algorithm, which turns that frequency finder into a factoring machine, the one that hands every encryption scheme in use today an expiration date. And finally the hard, honest part. Noise, decoherence, and the error correction that fights them. One number will follow us the entire way, and it is worth meeting right now. Every qubit you add doubles the number of amplitudes. 10 qubits is already 1,000 amplitudes. 20 is 1,000,000. 30 is 1,000,000,000 held in a single array. That explosion is two things at once. It is why a quantum computer might do what no ordinary one can. And it is why simulating one gets crushingly hard, why our little program will eventually strain your laptop, which is not a bug. It is you feeling the exponential with your own hands. So that is the invitation. Build it, run it, poke it. Change a phase and watch a bar you were counting on disappear. Add a qubit and watch the array double in length. Break something on purpose and see what the measurement does. Once you have built the machine yourself, out of arrays and matrices you fully understand, the words stop being incantations. Superposition, entanglement, interference, speed up. Each one becomes a specific thing that a specific line of code does to a specific array of numbers. There is one more thread I want to name before we start, because it runs quietly under everything. When you measure, one outcome happens and the rest vanish, weighted by those squared amplitudes. That rule is the most precisely tested number in all of science. But what it means, whether the outcomes you did not see were any less real, is a question the physics does not settle for us, and we will give it its due at the very end. For now, the machine is waiting, and it is only a length 2 array of complex numbers. Let us build it. What comes next is entirely in your hands.